Hello, this is Kevin. Welcome to my lecture on Chapter 9 of the Zelle 3rd edition Python programming book. Chapter 9 is about simulation and design. As usual, I'm going to leave the objectives for you to read on your own. And So there are two big ideas in this chapter. One is a simulation and the use of the Python random package and the functions within it to make simulation happen. Now, this won't be completely new to people in my class because I will have used the random package in previous tutorials, and so it's not going to be quite so new. The second idea is design. How to design and code and test and implement more complicated programs than we've been doing up until now. And this is probably going to be more new to people in my class. So simulation can solve real-world problems by modeling real-world processes to provide otherwise unobtainable information. Computer simulation is used to predict the weather, design aircraft, create special effects for movies, etc. And you'll notice that everything in that list is something that is either hard to do directly or impractical. So for instance, designing aircraft, they're really big things. And you could, for instance, do a lot of the design trade-off things by building a physical model and, for instance, putting it in a wind tunnel. And I'm sure that they do that. But you can also simulate those kinds of experiments digitally. And some of those simulations become more feasible to do many, many times. So that's the kind of thing that we can get through computer simulation that, again, wouldn't be practical to do at all or as often with more physical models. So we have a problem that we're trying to solve with the program for this chapter. And we have a racquetball player usually plays with people who are slightly better than that player and usually loses the match. Okay? And is a little bummed out by this, and it keeps asking, shouldn't players who are a little better win a little more often? And I think he really means here, shouldn't players who are a little worse than their opponent win more games? So one of his co-workers, Susan, suggests that they write a simulation to see if slight differences in ability can cause such large differences in scores. Okay? And, Danny, who has the question to begin with, maybe he's asking himself, does this happen to everybody, or, do I just choke? Is it just me? Okay? And of course, It's a little bit hard to simulate this. I mean, it's a little bit hard for him to run an experiment with himself because what he's really worried about is some other aspect. Has he got? Does he lose his concentration? Is he, you know, does he lose emotional stability when he plays? And that's the reason why he always seems to lose to people who are only slightly better, right? So this slide tells us about the rules for racquetball. When I think about this, I think of tennis because the rules are pretty similar for tennis. And I've only played a little bit of racquetball. So in my mind, I'm imagining more of a tennis match. So racquetball is played between two players using a racket to hit a ball in a four-walled court. One player starts the game by putting the ball in motion, serving the ball. Players try to alternate hitting the ball to keep it in play. This is referred to as a rally. The rally ends when one player fails to hit a legal shot. So either they miss it or they hit it in some way that's inconsistent with the rules. The player who misses the shot loses a rally. If the loser is a player who served, service passes to the other player, which is to say, if you win a point and it's not your serve, if you win a rally and it's not your serve, well then you don't win a point, you just get the serve back. If the server wins the rally, a point is awarded, so you can only earn points when it's your serve. The first player to reach 15 points wins the game. And there's no win by two. You're the first one to 15, you win. In our simulation, the ability level of the players will be represented by the probability that the player wins the rally when he or she serves. Example, players with a 60% probability win a point on 60% of their serves, or a 0.60 probability. So the value that we're going to give the program for the probability that they win the point is going to be a decimal fraction, somewhere between 0 and 1. Okay, so if we give 0.6, then that means that they're going to win 60%. The program will prompt the user to enter the service probability for both players and then simulate multiple games of racquetball. The program will then print a summary of the results. So here's what we're getting. We're getting the requirements for the racquetball program. Okay. Which the author calls, in the terms that he uses in the book, he calls this analysis and specification. So what's the input? Well, the program is going to prompt for and get the service probabilities of players A and B. The program is then going to prompt for and get the number of games to be simulated. So there are going to be three inputs. The probability that A is going to win on their serve, the probability that B is going to win on their serve, and the number of games to be simulated. And here's the output that we expect to get. So we're going to prompt at the console, what's the probability player A wins the serve? What's the probability player B wins serve? How many games to simulate? The program, sorry about that. The program prints out a nicely formatted report showing the number of games simulated, the number of wins, and the winning percentage for each player. So we said They played 500 games, wins for A, 268, wins for B, 232, and there's a 53 to 46 advantage for A. Okay? And one of the nice things about these digital simulations is you can run them a lot more times than it would be feasible to run a physical experiment. 500 games would take two players a very long time. And then we'd have to think about, just how their performance would change as they get tired, and whether one played well at night and one in the day. Are you going to play 500 straight games? That might kill two people, right? And yet the simulation, every time we simulate a game, we get two players and they're fresh as a daisy. Some notes. All inputs are assumed to be legal numeric values. No error or validity checking is required. Now, why are we saying that? Well, we just want to make the program a little easier to write. We know that we can check for legal values. We know, we can check that we're getting a proper numeric input and not some kind of alphabetic. But that's not what we're concentrating on in this particular program. In each simulated game, player A serves first. And I want you to remember that, because when we go to run the program and we see the behavior of the program, this is going to be a significant assumption, design choice. Okay? Okay, so I told you we're going to use the random library module from Python, and we are, and that produces these things called pseudorandom numbers. So let's see, when we say that player A wins 50% of the time, that doesn't mean that they win every other game. Rather, it's more like a coin toss. Overall, half of the time the coin will come up heads. The other half, it will come up tails. But one coin toss does not affect the next. It's possible to get 5 heads in a row. And in statistical terms, when we get the same value or the same range of values a number of times in a row, we call that a run. And generally thinking, unless we get 7 or more in a row, we don't doubt that we have a truly random process. So it is possible to get 5 heads in a row. Many simulations require events to occur with a certain likelihood. These sorts of simulations are called Monte Carlo simulations because the results depend on chance probabilities. Do you remember the chaos program from chapter 1? Well, who could forget it? We dove right into math when we didn't have to. The apparent randomness of the result came from repeatedly applying a function to generate a sequence of numbers. And the point here is that we've already seen a mathematical function that turns out results that seem to have a random kind of quality. So we shouldn't be surprised that it's possible to write an algorithm in Python to generate a series of random values. And it turns out that it is. A similar approach is used to generate random, technically pseudorandom numbers. A pseudorandom number generator works by starting with a seed value. This value is given to a function to produce a random number. The next time a random number is required, the current value is fed back into the function to produce a new number. Okay, So feeding back the last value that we got has a way of um, helping out the algorithm to produce random values. The sequence of numbers appears to be random, but if you start the process over again with the same seed number, you'll get the same sequence of random numbers. So in some programming languages, if you're calling whatever function that you use to generate pseudorandom numbers, every time you run the program, you get the same random sequence. Well, for you and I, that doesn't seem all that random because it's very predictable. But in Python, okay, the Python random library module, it's got a bunch of functions that we use for pseudorandom numbers, and these functions derive an initial seed value from the computer's date and time when the module is loaded. So each time a program is run, a different sequence of random numbers is produced. So this gives us a better experience than would have gotten some other or older programming languages. We don't have to know how to seed the random number generator because it's automatically done for us. The two functions of greatest interest are rand range and random. Okay, and there are more interesting functions than rand range and random, but these are the ones that he's using for the program at hand. In fact, two others that are of interest, one is called randint, which gives you a random integer value, and the other one is called choice, which gives you a random choice from a list of values. And again, if you're in my class, you've probably already seen those used in demonstrations that I've done in earlier tutorials and such. The randrange function is used to select a pseudorandom int from a given range. The syntax is similar to that of the range command. So randrange 1, 6 returns some number from the sequence 1 through 5. Why not 1 through 6? Well, you remember you remember how the second argument worked in the range function. The second argument is the first value that you don't want. And randrange 51055 returns a multiple of 5 between 5 and 100 inclusive. Ranges go up to but don't include the stopping value. Okay? And I've got to say that there's no way to describe the function of the second parameter. You can call it the end, you can call it the stop, but the fact is that's not where we stop. I think the best way to describe it, and you'll never hear the mothers and fathers of Python talk this way, is this second value is the first one that we don't want. Is that a stopping value? I don't know. So each call to randrange generates a new pseudo-random int. So again, we're using randrange 1, 6, and we get a 5, a 3, a 2, a 5, a 5, a 5, a 4. And again, these same values that we get multiple times in a row, that phenomenon is called a run statistically. And generally speaking, if we get a run that's fewer than 7 of the same thing in the row, we still believe that this is a random process. The value 5 comes up over half of the time, demonstrating the probabilistic nature of random numbers. Over time, this function will produce a uniform distribution, which means that all values will appear an approximately equal number of times. And one thing that's really nice is that when we're writing these programs, we usually pick how many times we want to run the simulation. And if we run it just a few, say 5 or 10, we can get really lopsided output. But the more times we run it, say 100 or 1,000 or 10,000 or 100,000 or a million, it'll take longer for the program to run. They run surprisingly fast, but we'll begin to see these. We'll begin to see the frequencies for the different values even out. The random function is used to generate pseudorandom floating point values. It takes no parameters and it returns values uniformly distributed between 0 and 1, including 0 but excluding 1. Okay? So we'll never get back a 1.0, but we will get back potentially a 0.0, and we can get back a 0.9999999. And you can see here that we're calling random and we're getting back values 0.79, 0.00, 0.13, 0.99, 0.21, 0.24, 0.73. So they're all over the place. The Racquetball simulation makes use of the random function to determine if a player has won a serve. Suppose a player's service probability is 70% or 0.7. So we want to come up with the Python for that. So we're saying if, and this is kind of pseudocode, if the player wins the serve, so there's got to be a comparison there, then we're going to bump up the score. He says score equals score plus 1. I would say score plus equal 1. We need to insert a probabilistic function that will succeed 70% of the time. Suppose we generate a random number between 0 and 1. Exactly 70% of the interval is to the left of 0.7. So 70% of the time the random number will be less than 0.7, and it will be greater than or equal to 0.7 the other 30% of the time. And that's exactly true because, of course, we're including 0, okay, but we're not including 1. Okay, so that's why it works out exactly. So the equal goes on the upper end since a random number generator can produce a 0 but not a 1. So if prob represents a poorly chosen variable name, no. I'm going to show you a version of the code where the variable names have been made more appropriate for people who actually are writing Python in the field, and so that in my version they're going to be longer. They're going to be whole words. They're going to be easier to read, but they might be a little bit worse at fitting onto the slide. And you have to give the author credit for making this code big, because like any other courseware developer, he wants the students in the back row to be able to see it. But this leads to some poor choices when it comes to variable names. So if the variable prob represents the probability of winning the serve, the condition random less than prob will succeed with the correct probability. So if we say if random, the call to random, is less than prob, bump up the score by 1. Okay, so that's the kind of introduction to the problem we're solving, to the tools that we're using. We're using the random package. Okay, and that's just a little bit of code that's going to help us to understand the program when we see it. Now, we're using one more thing in this chapter that we haven't really talked about, at least extensively, before. And this is an approach to design that he calls top-down design. And this has been a very popular approach to designing programs for certainly 50 years. I mean, a long time. And it's tried and true. And it's as good today as it was 50 years ago. And when we do this, we take a complex problem and we express it as a solution in terms of smaller, simpler problems. These smaller problems are then solved by expressing them in terms of smaller, simpler problems. This continues until the problems are trivial to solve. The little pieces are then put back together as the solution to the original problem. So these are the principles of top-down design. There's another phrase that's been popular, again, for 50 years, for taking the problem and breaking it down into pieces and then into smaller pieces and into smaller pieces. And that phrase is functional decomposition. So we take a piece of function and we decompose it into smaller parts and then smaller parts and smaller parts. I must confess that they chose the name before the popularity of all the autopsy shows. So these days, when people hear the word decomposition, they're more likely to think of rotting bodies at the body farm than they are to think of computer science principles. But this is also called functional decomposition. So top level design. So one pattern that we've used a lot and we've said is the input process output pattern. You know, every program has input and process and output, and it's usually helpful to use those to help to break the problem down. So here's some early pseudocode for the racquetball simulation. Print an introduction, get the inputs. Now he decides he's going to call these prob A, prob B, N. These are the variable names that he uses in his version of the program. My version, the variable names are going to be better when I refactor the code. Simulate endgames of racquetball using prob A and prob B. Print a report on the wins for player A and player B. So I think it's not hard to to see that this top level pseudocode is pretty broad brush, but it summarizes what the program has to do. Is this design too high level? Whatever we don't know how to do, we'll ignore for now. And I'm going to say it's not too high level if we fully intend to flesh out or add the details to these higher level descriptions as we proceed ahead with the method. Assume that all components needed to implement the algorithm have been written already, and your task is to finish this top level algorithm using those components, right? So, um, you have to think in a little bit of a magical way here. Or you almost have to think as a selfish designer. Okay, you have to kind of say to yourself, what if magically these parts were already built? Okay, well then, how would I coordinate them? How would I would orchestrate them? What are we headed for here? We're headed for the design of our code that's going to go into the function main. Okay. Okay. So in the top level design, first we print an introduction. This is easy, and we don't want to bother with it. So the top level design, again, is the code that we're going to put into main. And he says, let's just assume that we have a function that prints the introduction. He's going to call it print intro. Now, this, like a lot of the examples in this text, are not conforming Python names. So print intro should be in standard Python snake case. So I'm asking you to sort of entertain this, and I'll show you the more kind of industry-worthy version of the Python in a couple more minutes. So we assume that there's a print intro function that prints the instructions. Okay, and I guess we could do it one of two ways. I've seen people do this one of two ways. One is that let's say that they're typing the code in. So they assume they have a print intro function, and they just have a call to it, and that's going to raise an error until they add some code. The other thing that I'm very fond of is that as soon as you code a call to print intro, well, then you create an early version of print intro. The original name that we had for these things, we called them stubs. They were short little versions of the functions. Okay, so you could clear the error that you had in the code that you put into main by creating a stub version of print intro. Now, when are we finally going to put the code into print intro? Well, we'll get to it. Okay, that's what I like to do, because I don't like to see the in PyCharm we'll get a squiggly red underline when we have a call to something that we haven't coded a function implementation for. Okay. The next step is to get the inputs. We know how to do that. Let's assume there's already a component that can call get inputs. Okay. So what would we do? Well, we would call get inputs, and we would expect it to pass 3 values back. Okay. And of course, we know from the experience that we have in this course so far that when we pass 3 values back from a function, we're really passing a tuple, okay? But we're not even going to access the tuple. We're going to immediately unpack it into 3 values. And he uses the variables prob A, prob B, n. Okay? And again, in his version of the code so far, he's going to get a red squiggly underline that says he doesn't have an implementation for get inputs. But there's nothing to keep you from coding a stub for get inputs that doesn't have any real working code. And what would it return? Well, what I usually do is if we're expecting a decimal fraction between 0 and 1 for the first two, and we're expecting an int for the third, well, when I code the stub forget inputs, I probably would return 0.5 comma 0.5 comma 10. Okay? Now, is that what I'm always going to return? No. I'll eventually go back and I'll replace that code. Now we need to design simulate end games of Racquetball using the values of prob A and prob B. How would we do that? Well, we can put off writing this code by putting it into a function, sim end games. And again, this isn't a proper Python function name, and I'll show you the refactored version in a bit. And then we would add a call to the function in main. Okay. And we don't show that being added into main quite yet, but let's assume that it's there. And again, if you want to code a stub, well, code a stub. So if you were going to simulate the game by hand, what inputs would you need? I'm sorry. Here we are. Every time I move my mouse, that jumps around. I'm so sorry about that. Okay. If you were going to simulate the game by hand, what inputs would you need? Prob A, prob B, and N. What values would you get back? The number of games won by player A, the number of games won by player B. So this is really thoughtful. Okay. Okay, so we say no, these must be the outputs for the sim end games function. So we know what the inputs are, prob A and prob B and N, and now we know what the outputs are, number of games won by player A and number of games won by player B. Now, here I want to emphasize that in terms of outputs, okay, we're talking about return values. Now, functions can have other, kind of outputs in the sense that they could write output to the console. So they could do some kind of print. Or they could write output to a text file. They could do that with the print as well. But when we're talking about the inputs and outputs of a function, we're talking about the parameters in and the return values back. Okay? So let's continue on. So we now know that the main program must look like this. So there's a call to print intro. There's a call to get inputs that returns prob A, prob B, and N. And then there's a call to sim end games in which we pass in N, prob A, prob B, and we get back wins A and wins B. And again, when sim end games returns those two values, they're going to be a tuple. Okay. Are we interested in keeping the tuple? Well, right now it looks like not, because we immediately unpack them into wins A and wins B. What information would you need to be able to produce the output from the program? Well, you'd need to know how many wins there were for each player. These would be the inputs to the next function. And by the next function, we mean the one that prints the results. So we add on a final line here we call print summary. And again, you have to excuse the fact that it isn't a Pythonic function name. And what does it need to know? Well, it needs to know the value of wins A and wins B. And I'm just going to pause here because my slides have gone wonky, and I'll be right back. Okay, we're back. So, when we go to the next slide, we should be going here. So, the original problem has now been decomposed into 4 independent tasks. Print intro, get inputs, sim and games, print summary. The name, parameters, and expected return values of these functions have been specified. The information is known as the interface or the signature of the function. Okay, so the name of the function, the parameters that have to be passed into it, and the expected return values for each of the functions. It's called either their interface in a general sense. In some languages or some computer science practitioners would also call this the signature of the function. Okay. Again, when we're talking about the outputs, the return values, okay, those are the only things that we're going to document. Admittedly, functions can have other outputs. They can print things at the console. They can print things to files. They can also have other inputs in this sense. They can read things from the console. They can read things from files. But when we're doing this kind of module design, we're trying to concentrate on parameters in, return values back. Okay? Having this kind of information, the signatures or the interfaces, allows us to work on each of these pieces independently. For example, as far as main is concerned, how sim and game works is not a concern as long as passing the number of games and player probabilities to sim and games causes it to return the correct number of wins for each player. Now this is a real good point, and it's a point that we made earlier in the course. And we've said that when we're designing functions, we want them to have high cohesion. We want them to have low coupling. High cohesion means that everything in the function is about the same thing. It all has the same goal. Okay, and low coupling means that the calling code and the call code know as little about each other as possible. So one way for the calling code, main, to know as little as possible about the called code is for it to only rely on the interface, or in the language of the slide here, the signature. So it only knows about the parameters in expected and the return values back promised. Okay, so how could we add a design tool that would help us to do this kind of design thinking that could help us in a more graphical way to do this kind of apportionment of a function to various, when I say function, I probably should have said functionality. The functionality that we want to create to various functions within the program. And there is a tool called a structure chart or a hierarchy chart. And again, these have been around for a long time. They've been around for 50 years. They're still good tools today. We're going to tell you how to use them. So in a structure chart or a module hierarchy chart, each component in the design is a rectangle. A line connecting the two rectangles indicates that the one above uses the one below, calls it. The arrows and annotations show the interfaces between the components. So let's look at this. So we've got the modules in Python they include functions. Okay, so here we've got what, 5 rectangles for the 5 functions main, and then print intro, get inputs, sim end games, print summary. Okay, and the lines that connect them say the function on the top calls the function on the bottom of the line. And these lists of kind of variable names, I guess, are saying whether what is passed in and what is returned out. So for instance, print intro doesn't have any parameters in and doesn't have any return values back. So we don't see any variable names or arrows. Get inputs has no parameters in, and it's got 3 return values back, prob A, prob B, N. So we see them listed with a return arrow. Okay, sim end games has both parameters in and return values back. So prob A, prob B, N, their parameters in. Wins A, wins B, their return values back. And print summary has only parameters in. It's getting in wins A, wins B, and there's no return values back. Now, one of the nice things about these hierarchy charts, or structure charts as they're called, is that they give you the opportunity to document how you're going to distribute the functionality into functions. But more importantly, they document the interfaces. You know, what are the parameters in, what are the return values back. Okay. At each level of design, the interface, it tells us which details of the lower level are important. The general process of determining the important characteristics of something and ignoring the other details is called abstraction, a term often used in computer science. The top-down design process is a systematic method for discovering useful abstractions. Okay, so useful function designs. Okay, now once you document the top level and the level under it, okay, well now you have to apply this all over again. So the next step is to repeat the process for each of the modules defined in the previous step. The print intro function should print an introduction to the program. The code for this is straightforward. Okay, so here he's showing us some code for print intro. And again, please excuse any aspects of the code that are not up to our standards in our class. He does get all the code on the slide, and I can tell you as a courseware developer, that's a hard thing to do. In the second line, since we wanted double quotes around A and B, the string is enclosed in apostrophes. So this is the thing he did here. I don't know why he needed quotes around A and B anyway. In the rest of all this, he just calls them A and B. There are no quotes here. Since there are no new functions, there are no changes to the structure chart, which is to say, um, print intro is on the second level of the chart. It doesn't call anything, so there's nothing on level 3. Now we come to get inputs. We prompt for and get 3 values which are returned to the main program. Okay, and again, you have to excuse variable naming and all that kind of stuff, but again, we're not expecting any parameters in, and we're expecting to return 3 values back. So that does the job. This function simulates n games and a variable number of games and keeps track of how many wins there are for each player. Simulate n games sounds like a counted loop, and tracking wins sounds like a good job for an accumulator variable. Well, I just want to tell you that again, he uses accumulator variable in a general sense. The most trivial case of an accumulator variable is a counter, and I'd like to distinguish between accumulators and counters. And so I think what I would say, the way I would express it, is a good job for a counter variable. So this looks very pseudocodey here. Initialize wins A and wins B to 0. Loop n times, simulate a game. If player A wins that game, add 1 to wins A, else add 1 to wins B. Okay, I think that's very good pseudocode. Okay. So we already have the function signature. Well, we have that because we detailed this on the structure or hierarchy chart. Okay, so what do we have? Well, we're getting in n prob A, prob B. Okay. With this information, it's easy to get started. So he sets wins A and wins B to 0, and then he starts a counted loop for I in range n. The next thing we need to do is to simulate a game of racquetball. We're not sure how to do that, so let's put it off until later. Okay, now let's put it off until later. Is a code for, let's take all the assumptions about how we're going to simulate one game of racquetball and put that in its own function. Okay, so we put it off until later. Yeah, that has a kind of lazy sound, but hiding all the assumptions about how we simulate one game of racquetball into just one function, that has less of a lazy sound and more of a wise designer sound. So let's assume there's a function called sim1game. And again, this is not a typical snake case name, so we're going to overlook that for now. The inputs to sim1 game are easy. The probabilities for each player to win their serve. But what's the output? We need to know who won the game. How can we get this information? The easiest way is to pass back the final score. The player with the higher score wins and gets the accumulator, I'm going to call that a counter, incremented by 1. Okay, well, let's look at this. So we're in sim and games. Okay. And we're going to call sim1 game. Okay. And we're going to pass it probability A, probability B. What do we get? Score A, score B. So this is going to be the actual score, the point score from one game. And you'll remember the game's over when somebody gets to 15, right? So we're going to expect this score A and score B to have values that are between 0 and 15. And so now we can say if score A is greater than score B, wins A equals wins A plus 1. Else wins B equals wins B plus 1. Okay, and then we turn wins A and wins B. Now, ordinarily, I would say, what about the case where they tied? Well, it's not possible to tie a game, okay? The fact is, the first person who gets to 15 wins. So there's no chance to tie, okay? So when these scores come back, one of them's going to be 15, one's going to be less than 15. So it's okay to assume if A hasn't won, that B has. Okay, that's not true for all games. In fact, in the games that typically I give the class to do in their coding assignments, it's possible to tie. In which case, this code would have to be more sophisticated. Okay. All right, so we're going to update the structure chart to include sim1 game, okay? And again, we're documenting the interface, passed in as parameters, prob A and prob B, passed back as return values, score A and score B. Okay? So that's what we have so far. The next function that we need to write is sim1 game, where the logic of the racquetball rules lies. And here again, one of the nice things about having left the logic of the racquetball game to hide all the assumptions in one function is that one is that you can keep putting it off for a while. We kind of talked about that. That has a lazy kind of a sound to it. But the other one is you have all the assumptions about how the scoring and the mechanics of a game work in one place. And for instance, if you get them wrong, you only have to go to one place to fix them. So players keep doing rallies until the game is over, which implies the use of an indefinite loop. Since we don't know ahead of time how many rallies there will be before the game is over. Yeah, so that sounds like we're going to be using a while. We also need to keep track of the score and who's serving. The scores will be kept in two accumulators. Again, since we only go up by one, to me, they're counters. How do we keep track of who's serving? One approach is to use a string value that alternates between A or B, and that's what we eventually use. So here's some pseudo code and here's some actual code, okay? So we're going to initialize the scores to 0, set serving to A, loop while game is not over, simulate one serve of whichever player is serving, update the status of the game, return scores. Okay, so this is the beginning of the actual Python. So here we're setting the scores to 0, we set the serving to A, and then we have the while condition. Now what's that going to be? What's the while condition? Let's take the two scores and pass them to another function that returns true if the game is over and false if not. Now, why in the world would we want to do that? That sounds like a complication. And yet, it has a wisdom to it that we should see in a minute. Okay, so here's what we're proposing. That we have a function called game over, and we're going to pass in score A, score B, and we're going to get back a Boolean, true or false, if the game is over. Okay. Now, why might we want to do that? Well, there are times when the rules of something like this. So it could be quite complex. It turns out that they're pretty simple, and we could have coded them inline, but this is a nice illustration of how to do this, right? So we can take all the complexities of deciding when the game's over and hide them in the function game over and get a simple answer back. And what's that going to do? Well, that's going to simplify the condition on the while statement in Sim1 game. Okay? And it's a nice technique to learn. Okay, so here we go. Here's the code for Sim1 game now. Okay. And again, there's a lot of comments here, and you'll see in my refactored version that I've stripped out all of the comments. And why? Well, because these comments are kind of teachers' notes. Oh, okay. This is not the kind of thing that we leave in code that we're going to code in our day job, because people don't maintain these kind of comments. And to the extent that it changes over the life, we get these kind of play-by-play comments that get out of date, okay? So one of the things that we learn as we get more sophisticated as a programmer is the best way to know about what a code does is to read it. And one important measure of the goodness of code is how easy it is to understand what it does by reading it. So these kind of play-by-play comments, they're excusable for an instructor who wants to remind her or himself to make these points, but they'd be a crutch for a programmer doing this in their day job. So we set serving to A, we initialize the score counters to 0, and then we can say while not game over. So game over is a call to a function that takes on the value true or false, and we pass in score A and B. So you can see how nice that is. Now, would it be a lot more complex to just move the comparison code up here? Yeah, it'd be harder to read. It's not horrible to read, though. I think it was an opportunity to show you a technique. Inside the loop, where we haven't coded yet, we need to do a single serve. We'll compare a random number to the provided probability to determine if the server wins the point. Okay, so we do random, we get a random value, and if it's less than the probability value, well then they've won the point. The probability we use is determined by whom is serving. I think it's who is serving, contained in the variable serving. Okay, so if A is serving, we'll use A's probability, and based on the result of the serve, either update A's score or change the service to B. Remember, a player can only increase their score when they win a point while they're serving. If they lose a point, then the serve just goes to the other player. So we say if random is less than prob A, well then A won that point, so we increment score A by 1. Else, we turn serving to B. Okay. And here's all the code. Else, if A is not serving, which means that B is, if random is less than prob B, then B wins the serve. We increment the score count for score B, and else B lost the serve, and we turn serving to A. what I like is that this whole concept of you can only win a point when you're serving and the serve goes back and forth. It seems really complex and you would think it'd be hard to code, but we've broken into two components here: who's serving and the probability and this kind of stuff. And this turns out to be not simple code, but not nearly so complex as I had thought that it would be. Okay, so putting the function together, it looks like this. So again, we don't need all these comments, but the parameters in are prob A and prob B, and we are returning score A and score B. And again, we don't see any logic in here about what the score has to be for the game to be over, because we delegated that to this game over function. Okay, this is one tricky function left, game over. Here's what we know. We're passing in, again, these are not good variable names, A's score and B's score, and we're going to return true if one of them has gotten to 15. Okay. We can check this with a Boolean. So A equal 15 or B equal 15. Okay, either of those will work. Okay, so let's see how that looks. Well, what's interesting, again, these comments are just a teacher's crutch. Return A equal 15 or B equal 15. So if A has gotten to 15 or B has gotten to 15, we're going to return true. And now we've thrown, I'm sorry, I lost it again. We've thrown in the code here for print summary. We're getting in wins A and wins B, okay? We are reconstituting N. This is interesting, okay? N is the number of games, okay? And we are going to print the number of games, N, okay? We could have passed N in, okay, explicitly. But the author says, isn't N just the sum of wins A and wins B? Let's pass one fewer parameter and just reconstitute it here by calculating N again as the sum of wins A and wins B. And then we've got 3 prints, one where we have the total games and the rest of it. Okay. And the formatting that's done here is, again, this is a version of Python formatting that uses a call to the format method of the string class. And this is, of the 4 ways to format in Python, this is the third of the 4th. This was the contemporary one when the textbook was written, but has been superseded subsequently by F strings. And in my refactored version, I'll show you the F string equivalent. Okay. Okay, so let's pause here, okay, and show you a cleaned up version of this code, okay? Just because I think it's the right thing to do. Okay, so what we had seen, the code that came with the book is called, the program is called RBall, okay? And it pretty much has the code that we just saw. The problems it has are many. One is that, for instance, we don't have 2 blank lines surrounding functions because of the fact that textbook authors want to cram as much on a page as they can. Um, the variable names are not properly formed Python variable names. This has to do with the fact that I think these programs were translated or adapted from perhaps Java text. So they're just not Pythonic. Okay, so that's true of the variable names and that's true of the function names. And then printing wise, we're using, where's the printing? We're using calls to the format method of the string class instead of using Python f strings, which were introduced in Python 3.7. Okay. Uh, you'll notice also that the author has used this more sophisticated version of the call to main, which kind of indicates that he thinks that he might want to use this as a library and import it, which I'm not particularly fond of. So what happens when you refactor this? Well, again, the comments up top turn into a simple doc string. We have a regular import. Okay. Now let's look at the names of each of the functions. Main hasn't been changed. That's a good practice. The printing function is now called print introduction in snake case. Get inputs has been put into snake case. Simulate end games has been put into snake case. Simulate one game has been put into snake case. Is game over? There's a good practice for functions that return a Boolean that's been used in several programming languages in which we make the name of the function a question. Okay, that's going to return an answer, yeah, true or false. So I decided to refactor this, so it's now called is game over. Okay, and then print summary has been put into snake case as well. I left this version here where he's checking if he doesn't want main to run if this thing has been imported in. Again, for me, I typically would just have a call to main, but I left it there. And let's look at things that have been changed. One of the things that happens is that if you look at main, it reads better now. So we can say that when we call get inputs, we get probability A wins, probability B wins, and wasn't that bad of a name. Again, when we call simulate end games, what do we get back? Again, I think he was calling them A and B. Now they're called games 1A, games 1B. And then print summary, games 1A, games 1B. So with a little bit better job of naming the variables and naming the functions, we get a story that's easier to read. Sorry about that. We get a story that's easier to read, and we don't really need all these comments. Print introduction hasn't changed a lot. I think I took A and B out of double quotes because I think they were dumb. Get inputs. I cleaned up the language of these two prompts. They were shortened, I guess, to make them fit on a page, and I made them more user-friendly. One of the things that you'll see when you look at these is that Uh, the names that I use as formal parameters in each of the functions are different than the names that they're being called with. So simulate M games. Um, uh, we're calling with probability A wins, probability B wins. And when I picked them up, I gave them Carlo names, A win probability, B win probability. I always want to emphasize to students that these are not the same variables. Okay, when you give them the same name, beginners sometimes get confused. Um, when we are bumping up the score here, I probably like us to do a plus equal rather than this, because I try to get people to standardize on that. So I probably think we want to change that. Okay, that's a little more standard. And then down here, when we're doing the score and simulate one game, same thing. Let's give that a plus equal as well. That's a little more modern, I think. Okay. Now, do you have to do that change? No, I don't think so. Just, again, your code should have a consistency from program to program. So when people are reading your body of work, they know what to expect. Okay, so we've got that. Simulate one game. Is game over? Same deal. Okay. And then print summary. I've turned these into F strings. Okay. And I did a couple of things. One is I wanted to simulate a lot of games. So in the number of games simulated, I wanted to add comma separators, because I wanted to make it easy to read a million if I ran a million games. And I wanted to add comma separators into the number of games won by each of the players. So I've added that there. Okay, those are all the changes I've made. Okay, so let's test this program and see how it behaves. Okay, all right, so what's the probability that player A wins a serve? Let's say it's 0.6. And let's say the probability that B wins the serve, it's 0.5. And how many games to simulate? Let's say 1,000. Okay. And as you can see, there's not a lot of difference. It's only a 10% probability difference between the two players. Okay, but then there's a really lopsided outcome where A wins 80% of the time and B wins only 20% of the time. So this is consistent with the observations that are in the book, and I think I have a slide or two on that. Now, and so Danny Dibblebit, who commissioned the work, can kind of rest easy that it's not really his kind of personal failing that he loses so badly to players that are only a little bit better than he is, because that's sort of to be expected mathematically. Now, I'll show you an interesting phenomenon that has to do with a bias that's in the way that this simulation has been done. Okay. So I would think that we would think if these people were equally good, that they should do equally well, right? So the player A is going to win their serve 60% of the time, 0.6. player B 60% of the time, 0.6. How many games to simulate? Let's say 1,000. Okay. And we're seeing that even when they've got equal capability, player A wins 54% to 45%. What's that? Well, it turns out the player that goes first has an advantage. And this is true in a lot of games. And there are usually rules about how we trade back who serves first and that kind of stuff. It often goes to the winner of the previous game and those kinds of things. But there are rules about that, and there's a bias in this when we always have A serve first. Okay, so what's interesting here is so this is true if we do it. We'll get the same answers if we run this 1,000,000 times. So let's say 0.6, 0.6, and then let's run this 1,000,000 times. 1, 3 zeros, 3 zeros. So it takes a little while longer to come back. So here we go. So it's still 5346, pretty much the same thing. Okay, so it's not the number of games. You can see by the time we've run 1,000 games, we've probably gotten most of the benefits of running a lot of simulated games. Okay. Okay, so let's look at this. So one of the things I would say to player B, if that were Denny Dibblebit, I would say the next time you play, just say, how about I serve first? Okay, because let's look at this. If player A wins 59% of the time, okay, and player B wins 60% of the time, and let's do 1,000 of these. Player B just has enough to win. They're winning 50.2 over 49.8. So these small differences in ability can offset the player A serving first advantage. But I just would say, if I were one of the players, I'd say, hey, how about I serve first this time? Okay, so let's see. There's a couple more points to be made, and I'm going to try to make them about this. So let's talk about how we designed this. We started at the highest level of our structure chart and worked our way down. At each level, we began a general algorithm and refined it into precise code. So pseudo code, then code. This process is sometimes called stepwise refinement. And that's a common phrase. So here's this. So stepwise refinement, we could summarize it. Express the algorithm as a series of smaller problems. Develop an interface for each of the small problems. Detail the algorithm by expressing it in terms of its interfaces with the smaller problems. Repeat the process for each smaller problem. So 3, okay, one way to detail that is to create a structure or module hierarchy chart where you can express the details of the interfaces. What are their parameters in? What are the return values back? So I just want to pause here and say, does everybody create a structure or module hierarchy chart every time they write a complex program? The answer is no. Okay. there are some people who do their top-down design. Um, they have a kind of a rough sketch of the problem. They might sketch out a rough hierarchy chart, and then they might just start to write the code from top to bottom. That's top-down design and top-down implementation. Okay, and in my tutorials, I kind of show you that process. Well, when would it be important to write to actually author uh, a structure or a hierarchy chart? I do it when I'm trying to build something that's really different. I really want to understand the pieces. A lot of the problems that we solve, they might be complex, but they're a lot like a problem that we've already solved. Okay? And we kind of understand what the parts are going to be and how they relate to each other. So the value of coming up with so detailed of a sketch before we begin to code is probably smaller there than in situations when we're building, a whole new kind of animal. Right? So you have to decide whether you're going to sketch out a structure chart, or whether you're going to fill in every bit of it or not. And that's going to come over time. That's going to come with how much value that throws off for you. Now, bottom-up implementation. Even though we've been careful with the design, there's no guarantee we haven't introduced some silly errors. Implementation is best done in small pieces. A good way to systematically test the implementation of a modestly sized program is start at the lowest levels of the structure, testing each component as it's completed. For example, we can import our program and execute various routines or functions to ensure that they work properly. Well, that's why he wanted this code at the bottom. So he wanted to be able to import this and have some test code in another program, which is the thing that this author likes to do. We could start with the game over function. So he could import the program and he could call game over and see what the results are. Okay. Notice that we've tested game over for all the important cases. Okay, well, probably have. Now that we see that game over is working, we can go to sim one game. Okay, so you get the idea. One way to do this is to design it from the top down and to implement it from the bottom up. I've got to say that that's an old-fashioned idea. Okay? Now, one of the nice things about implementing things from the bottom up is that when you're testing the higher level functions, you never have to come up with a stubbed out or phony version of the lower level function because they're already built. Okay? And that's one of the things that makes this such an appealing way to do it. Is that what people really do in the field now? I would say that generally they don't. Okay? Generally they design from the top down and they write the code from the top down, and that means that every time they write the code for a particular level, they need to have something to test with, and what they typically do is that they write stub versions of all of the functions at a lower level that haven't been implemented yet. This is a practice that I demonstrate in my tutorials, and I would say that generally that this is the more common practice in the field today if you were to go look at what's done by working coders. So this is a little more detail on how you would test from the bottom up. So here's the discussion of the results. I think I've already discussed those pretty well, and I've uncovered the bias that there's a built-in advantage for the person who goes first. But apart from that, I think that Denny's uh, uh, worry over, is it realistic that small differences in ability can turn into big differences in results. Well, we just have to look at this. We'll try this one more time, and we'll say the probability that player A wins the serve. Let's say that he's player A, he gets the serve, and he only wins 55% of his, and player B wins 60%, and we're going to do 1,000 games. You can see that player B, even having given away the slight advantage that you get by serving first, he still beats the lesser player who's pretty close in ability. Okay, so that's the answer, and that would be very hard to get at by other means. All right. Now, there's a discussion at the end of the chapter that I kind of like, and I kind of don't. So I'm about to go on to it now. Okay. It says, well, no, do we always want to do design the way that we talked about earlier in the chapter, which is to do a thorough top-down design, and to do, to design, to design the whole program before we create the code, and to do it from the top down. And he talks about other approaches. He talks about prototyping and spiral development. And they're different in a couple of ways. One is that we do have to ask ourselves, are we going to try to write the program that meets every imaginable requirement right out of the box? Or are we going to come up with a program that meets some of the requirements first and get that to work, and then create version 2, which meets more of the requirements, and create version 3 that meets more of the requirements? And so there have been three kind of movements in programming and systems analysis over the last 40 years. The first one was called prototyping. So the idea is we would build versions of whatever the product was and show it to our client and get feedback, and then we decide where we wanted to go. Did we want to add extra features or change the ones that we had? So it was called prototyping. Okay. Then it was sort of enhanced by this approach that people called spiral development, which was seeing development as a series of prototypes. So there was no expectation that the first prototype that you built would be the last one. Okay. And I'd like to point out that that's been taken even further, although it's not mentioned in the book explicitly, is that there is a newer approach that's been around in the last 20 years that's called Agile software development, in which we, again, we don't assume that we know all the requirements. And so we commit to build one part, and then we get feedback from the client, and then we commit to the next part, and then the next part, and then the next part. So it's kind of the mature version of spiral development. It's called Agile software development. Now, the question is this real different than what we just learned? I'm going to point out that these really are differences in deciding what we're going to build. Okay, what are the requirements for the program? Okay, are we going to try to get them all understood up front and expect just one development process? Or are we going to see this as a series of kind of conversations with a client? Okay, now I think that changes what you're trying to build at any one point, but how you build it's going to probably be the same thing. So the top-down things that we talked about earlier are going to apply to anything that you're trying to build in the moment. Okay? At any given moment, you're trying to build either one thing or that thing with more features. Okay? And this kind of top-down approach is equally applicable no matter how many versions you're going to build. He goes on to talk about how you might take something like the racquetball game and not develop all the features at one time. So you might say, maybe the first version, write a prototype where you assume there's a 50-50 chance of winning any given point and 30 rallies. Add on to the prototype in stages including awarding of points, change of servants, different probabilities. And he kind of goes through how you might do that. The program could be enhanced in phases. So he shows us a phase 1, then a phase 2, then a phase 3, then a phase 4, then a phase 5. Okay. Now, again, these are not really differences in how you build any particular program, but sort of more general approaches to how you manage a project and how you work in systems analysis with a client to understand the requirements. So, again, this is interesting stuff. And of course, I teach a course in systems analysis and occasionally a course in project management where we really deal with these kind of issues a lot. But here, I just want to emphasize that the basic approach that we took to designing and implementing a program top-down has been a promising approach for a long time for how to design and build a more complex program. And it continues to be the most popular approach used by practitioners in the field still today. And let's see whether we have anything more to say. Okay, so just a couple of closing comments from the author of the book on the art of designing a program. The spiral stuff I won't talk about. Good design is as much creative process as science, and as such there are no hard and fast rules. And I think he's talking about here about how we design, how we make systems analysis decisions. The best advice: practice, practice, practice. And I couldn't agree more. The more things that we build, the more chance that we get to show them to clients and get their feedback, the better we get at this art. That's it. So I'm going to say bye until next time. Bye-bye.